So let me start again. Thank you all for coming, and I'm really pleased by this attendance. I'd love to hear from as many of you as possible over the course of this, and I'm not quite sure how the best way to make sure that happens is. I've never run kind of a breakout session like this before, especially over Zoom. So
So Brad, my recommendation to you is to just click on the participants thing, and then if people want to use the raise hand function to ask a question, then you can just look for the blue hands.
Okay.
That's probably the best way to manage it, given how many people we have in the room.
Great. Thanks, John. Right. So I put together a very short agenda. It's just 2 slides. And my rough thinking was that we would kind of split this into 2 pieces. The first piece would be kind of a near-focused thing where we would discuss what we want to do, what we would want to do with an LRIS replacement, LRIS-2, and what, sorry, that's not quite the right way to put it. What are the key capabilities that we think that LRIS as it currently has is missing? Sort of the sort of near-term things that you would like to see fixed tomorrow. And then the second part is I'm more thinking of here's some technologies that we think are going to be coming down the line. And if you had that technology on an LRIS-like instrument, how would you use that? What kind of science would you do? So the sort of first part, I'm thinking of the science you're currently doing with LRIS. How could we make it better? And then the second one is, here are some possibilities for new things we could do, new capabilities that we could add to LRIS. And then how would we actually use those capabilities? Right, so I'll actually share my screen here. And so the first one is, the way I'm thinking about this is, what does the Keck SSC need to hear about LRIS? What are the things, the gripes that you have? And some of these, you say, oh, well, everybody knows, Brad, that it's not stable because of the current mechanical instability. We have to take calibrations at very specific position angles and elevations with the telescope, and that really limits certain kinds of science. Transient spectroscopy is sort of a classic example where you'd want to be able to take a spectrum and reduce it as quickly as possible, and you can't use the calibrations taken at the beginning of the night, so you have to then wait till the end of the night to get calibrations at the right position, or use up precious dark time taking calibrations at the position of the target on the sky. But I would like to be able to hear this from you folks so that I could get, the feedback to make sure that I know, I have a very particular bias based on the kinds of science I've done. And so I've put down a couple bullet points: stability, sensitivity, flexibility. And in the Slack channel, some of you have actually started to address this. But I would love to hear from you folks who have actually used the instrument. What sort of things that you think we really need to fix on it now, just to make sure that we have all of that understood. And then going forward, as I said, in the sort of second half of this, I'd like to start to do the more pie in the sky things, like what would we do with some additional new capabilities? So if anyone has any thoughts that they'd like to start off with, feel free to go ahead. I'm going to stop sharing my screen. And all right, Josh has already raised his hand. So do I need to unmute Josh, or can Josh just unmute himself and talk?
Can you guys hear me now?
Yes.
Great. So one thing that I think would be good to keep in mind is that the current use of LRIS, there's a lot of single object spectroscopy and a lot of time domain follow-up. So I think one of your bullets should be speed and efficiency. So that's readout time for the detectors and reconfiguration time if you're going to go to multiple configurations. You know, because if you're taking hour-long integrations, an extra couple of minutes on reconfiguration or readout's no big deal. But if you're doing very short integrations, that really hits your efficiency. And I see that a lot when people come and use LRIS. To the point where I've had some observers suggest that, you know, using like frame transfer CCDs to take a single object spectrum, shift the pixels down to a masked part of the CCD, and then start your next exposure while reading that out would be a neat feature.
Okay, John raised his hand.
Yeah, I wanted to underscore a point that I put in the Slack, and I think Josh pointed this out as well, and I'm sure a few others will, is that the idea of moving towards a MOSFire-like slit mask configuration to really open up possibilities during the night, even something as you know, the potential of doing an image followed by a reconfig of the slit mask could be a quite powerful tool. And since it's not going to be cryogenic, I think we can retire some of the concerns about that. So I think the ability to move away from masks and moving more towards something like a bars configuration would be a really powerful addition to it and would open up a lot of flexibility. The other aspect I would love to see is a rather high resolution mode with one of the gratings, just because I can imagine a world, and as much as it pains me to say it, I can imagine a world where perhaps high res doesn't need to be on the K1 deck if you have KPF plus high resolution capabilities with LRIS that go down into the very blue where KPF can't, and where we could, you know, just have, you wouldn't have the full throw that high res does, but you could capture some of the high resolution capabilities. And given the throughput of LRIS, those high resolution capabilities could be really interested for things like supernova follow-up if you got them early enough, et cetera, et cetera. So those would be my two requests: is an RF 20,000+ mode and a bar-like slit mask system.
Can I make a couple comments about your statements, John?
Yeah.
One is, I mean, obviously, a configurable slit unit like we use for MOSFire is great for flexibility, but if you know you just want a slit, a long slit, and you want it configured as fast as possible, using a mask is going to be a lot faster. So
okay.
it slows, so it's kind of works against the, quick, ready to observe mode that some are asking about.
How much is the speed limitation of the bars due to the fact that it's a cryogenic system? So, you know, if I wanted to turn the bars into a long slit and it wasn't cryo, do you get a significant speed up over MOSFire?
You could, I mean, if mechanically it will run at twice the speed, but it was never tested that way, and it was believed that it would shorten the lifetime of the. Actually, I worry about a similar kind of mechanism if it's not cryogenic, just because it would be really susceptible to filth accumulating. And I think that would be dangerous to that kind of a gizmo. And the nice thing about cryogenic is that it's never exposed to the elements. But it's something to think about. I mean, I think the main downside of such a device is cost. I think we're talking about $3 million just for the CSU.
So Chuck makes a good point about the speed, because it would affect the acquisition speed as well. With a mirrored slit, you point your guide camera at it and you just drop your visible target in the slit. With a CSU, it's a little more complicated unless you can get a mirrored CSU. So that's definitely something to consider.
So I wanted to ask people about readout time. Is that, so if right now at least the blue side is about 40 seconds in the mode that most people use. And so you're always limited by the speed of the red side readout. which is much slower. Is 40 seconds too long? I mean, do you find that being a source of significant overhead? Because it would be easy to imagine using a frame transfer kind of mode for a slit that's not the full length of the field of view.
I know of certain science cases that would want something like that. I was asked in the Slack channel about exoplanet transmission spectroscopy. And that's the kind of thing where you would want, you could get away with a very small slit, but having some sort of frame transfer or just direct charge tracking would be, charge transfer would be really good to get the sort of time resolution that you want for that kind of science. But that's a pretty specialized case.
I wanted to make just to mention what we think some of the constraints are for a low-res 2, and that's it kind of has to go on Keck 1 Cassegrain unless we want to reinvent the ADC, and we don't have a Naismith position for the instrument anywhere, so it more or less has to be CAS, and you know, Keck 1 CAS has I don't think we're too constrained within reason on the field of view. You know, if it were something similar to the current LRIS, is that good enough, or too overkill, or something else? You know, it's got currently about 7.5 arc-minute slit length. Does anyone care about the multiplexed mode of LRIS in this?
I mean, I'm looking, and there are people I know who have used multi-object spectrographs with much bigger field of views in the section in the participant list. I'm hoping we can get some of them to express opinions. I mean, they might just say, "Oh, I'll just use demos." I don't know, but.
So I have a very specialized use case. I do astrometry of potential asteroid impactors. So I use LRIS in imaging mode, where I usually would take 60-second exposures or shorter if it's a very fast-moving asteroid. So having a readout time in imaging mode comparable to my exposure time is a little bit frustrating because I lose half of my time to overhead.
Yeah, that's painful.
Melissa, do you have strong requests on field of view, or?
Usually by the time the asteroids get to be about 24.5 magnitude, we know pretty much where they are. We just don't know precisely enough where they're going to be 20 years from now to know if they're going to hit us or not. We know where they are right now.
So I've always liked LRIS field of view, which is sort of I mean, for a lot of what I do, DEMOS is sort of overkill in terms of field of view. And so having that, like the current field of view of LRIS is nice for what I do. But I could always use DEMOS, and I have done so with, you know, just a very sparse collection of slits on the outer portions. But that always seems to me to be a little bit of a waste.
Can I ask you a question, Chris?
Sure.
When we were discussing these CSU-like setup for Mossfire, is that gonna, one of the great things about LRIS, maybe too good, is that you can design any mask you want, even if it's not like physically machinable, I think. Having the much more fixed format of the CSU of Mossfire, would that actually get in the way of some of your science?
For me, possibly. I think I've never done anything too crazy with the slits on a slit mask, and so I don't think. I mean, I think the CSU could be fine for what I would like to do, but you know, I think also the science I'm looking at is changing, and so it might be, you know, advantageous to be able to, you know, mill slits that would not be possible in the CSU. I know I'm sort of in a transition between what I used to do and what I'm going to be doing, and so I haven't thought about this that deeply yet.
Okay. Yeah, I'm looking at Danielle Berg's background and looking at those arcs and thinking, could you do that with the Mossfire CSU? Could you, you know, you can mill any kind of shape you want, so you could be able to place an arclet that's curved easily into a focal plane, but you can't. Could you do that with the Mossfire CSU or not?
No, absolutely not. Not unless you had quantization at the 1 arcsecond level,
Right.
which would be extremely inefficient and expensive.
But for bizarre shaped objects like that, would we get the science going to LRIS as opposed to KCWI plus KCRM?
Depends on how many arclets you want to look at. You know, cluster fields of view are on the order of a few arc minutes. So you could do it with KCWI and KCRM by tiling your way across, or you would observe, you know, 10 of them in one mask and 10 of them in another mask. It's, once again, it's a relatively specialized science case. But galaxy lensing, yeah, I think KCWI is kind of the natural thing to do.
Speaking of KCWI, in order to get resolution anywhere close to 20,000 with a slit spectrograph, you would need to have a slicer, which means because, you know, basically the map, at least if you did, unless you changed something really extremely about the configure, like, you know, for example, on KCWI, the slices are about 0.28 arc seconds in the mode that gives you a resolution of 20,000. And that's kind of pushing it to the maximum you can get out of something that has a beam size of 150 millimeters. And it's sort of the same kind of configuration that all the current imaging spectrographs have at Keck. So you could use such a thing for single target observations. It would be more of a slicer and less of an IFU, in the sense that you just have to get the slit to be narrow enough to give you the spectral resolution you want. Is 20,000 the number? That's the one that John mentioned.
I've heard other people mention it too, so.
It's pretty challenging. The spectral coverage would be very small. And I don't think you want to try to put a cross-dispersed instrument inside of a conventional single-order spectrograph.
No. All right. I'm sorry. I'm not paying sufficient attention to things. Sarah White has had her hand up for a while, I suspect. Could you?
It's okay. Thank you, Brad. So going back to your question about the science case for a large field of view, just for people to bear in mind all of these radio surveys that are being conducted. And these are like large area surveys, whole sky. So it's really useful to have several spectra, obviously with over a large area. One of my samples at the moment, I'm following up using the Southern African Large Telescope, because that's where I'm based here in Cape Town, my radio sources are like 1 per 1 square degree, but they're distributed over the whole sky. So maybe, this is a bit too extreme. I was just wondering, how large would you go beyond like 7 by 7 arc minutes?
Well, the telescope's 20 arc minutes, so that's a limit. And then for covering the full field of view of the telescope, our goal or plan is to build something called Phobos, which will cover that full 20 arc minutes with fibers or fiber bundles. And that's kind of our wide field, really wide field spectrograph. Connie, you've had your hand up for a while.
It was just to ask for a little, to circle back to this question about fast configuration time, because the other way to try and push the configuration time is to be, to try and speed up the time it takes to go from imaging mode to having the long slit in the field, right? So that's another knob to turn in the design. So I was asking whether, I guess, John's point about configuration speed was about flexibility or speed, really, because it's still speeding up the switch between open and a mask is still limited to whatever's in the wheel or the slide or whatever you decide to do, right? So I guess my question is, is it about speed or flexibility or both?
For me, the issue of bars was flexibility, not speed. But for others,
so it would be the option to do multiple targets and assign the slits on the fly.
Yeah, either on the fly or just not be constrained to knowing that you've only got 6 masks or things. Because, when I guess when presented with marginal weather conditions, for example, you oftentimes just dump your slit mask game and you switch to long slit, and having a happy middle capability by configuring on the fly is or going to a backup program that has more flexibility to it than what a fixed set of masks provides, because we usually design our masks for, we're going after RF24 stuff and we want to go after super faint things, and or a single set. But it's more of convenience. But I think a lot of the points Chuck raises about bars and a lot of the questions about configuration speed for people who want to be doing many targets in a night is a trade space that we have to look at. And we shouldn't neglect the capabilities of what Phobos would be doing on Keck 2. And perhaps that is, the place to consider that the trade space is maybe happening over the fact that we can configure the fibers on Phobos on the sky and, create big IFU bundles with them or whatever. And that's really where the flexibility should lie. But, LRIS goes down to or LRIS-2 presumably will go down to the atmospheric cutoff. And so that's a place where we want to live. So
if LRIS-2 is as configurable as LRIS-1 is, and it uses VPH gratings instead of prisms and reflection gratings, the actual time to switch modes is going to be slower than the current LRIS, I think. Or at least, I don't know, the way I observe with LRIS is I've set the red side up how I want it, and I only use the blue side for acquisition and everything else because it's so much faster. And the problem with VPH gratings, to go from imaging to spectroscopy, you actually have to change the camera angle. Or at least, if you don't have to change the camera angle, you have to have some kind of mirror at some angle other than that's different from the grating angle to get the light where you want it. So that it's actually, if you're using one configuration for everything you're doing, then it could be fine. If you're changing, optimizing wavelength. For people who've used KCWI, you're used to thinking about this. You don't want to use an infinite number of different setups in a given night.
Right.
But you know, where's the happy medium between what's the right word for it? I hate to say flexibility because I always think of flexure, agility, and you know, it has to at some level be a lot of things to a lot of people. And right now, what low-res is good at is throughput, and what it's not so good at is stability. And I think we could fairly easily make an instrument that's both stable and high throughput, and could be optimized, you know, by the use of color channels in the same way. It could be optimized over the whole optical passband from from the atmosphere cutoff out to a micron. I'm told by Mark Cassis that it's something like 40% of current low-res observations are single slit.
Yeah.
Yeah.
That's still that means people are actually using the multi-slit capability 60% of the time, if I did my math right. So I wonder if that's going to continue to be true into the future.
I think the other question that, and I'm sorry to dominate when I see Randy's hand is up, is just a question that pops into my mind when you talk about the long slit versus multi-slit is, how frequently are we still using LRIS for imaging? And is there a different type of imaging that we want to be thinking about with LRIS-2 in terms of number of filters or types of filters? You know, can we get kind of weird with filters or think differently about filters on an LRIS-2 versus LRIS?
Like the ramp filters or something like
yeah,
that?
Ramp filters was where I was going, but
yeah.
Well, you can make any narrowband filter into a ramp filter if you have control of the tilt, which you could if you put imaging filters in a grading holder on a VPH based.
I think you just gave me a headache, Chuck.
Because we thought about the same thing for WFOS on TNT.
Okay. All right, I'm gonna say we should let Randy lower his hand.
Well, I had a couple points to make, and one was similar to what Chuck was saying, and that I think historically LRIS's strength has been its agility and its general purpose, and it's, you know, able to change gratings and filters and change almost everything in the instrument over the years, and it's served a lot of different science programs. And so I would side more towards agility as opposed to switching modes fast, if that was the trade-off. And the other point I was going to make, that if we do decommission high res after KPF gets going, it would open up the Keck 1 Naismith platform, if that might allow for you know, a different restrictions on flexure and things like that for a future LRIS-2.
So putting LRIS-2 on a K1 Naismith deck, obviously flexure becomes easier, but field of view becomes more restricted because the deployable tertiary doesn't illuminate. I think it stops at 5 arc minutes, something like that.
Yeah,
I think that's
right.
about right.
Yeah, that's the other reason to put it at CAS, is the field of view can be bigger.
And then we would have to build an EDC for the new one.
And have an extra reflection. Well, maybe not. Depends on how it's laid out. I mean, the main thing that limits low res, you know, people complain about the image quality in low res compared to other instruments at Keck, and it's really is because, well, there are two reasons. One is that it's never really in focus because the instrument flexes so much that focusing in one place will be a little bit different than it will someplace else. But really, you know, where it is in the focal plane of the telescope, you can't get images better than 0.4 arcsecond full width half max. It's just the telescope images are not any better than that, even when the seeing's perfect. And we could very much improve on that by bringing the field of view on the optical axis of the telescope, which would be a lot better for future GLAO. So that, I mean, that Brad talked about that in his presentation this morning. And it's actually non-trivial on a telescope like Keck to have an on-axis spectrograph, because it kind of forces you to having a huge transmitting collimator, which is not very efficient. And that's why the solution of these reflecting collimators was used for ESI, low res, and DEMOS. It's the highest throughput way of getting the light from someplace in the focal surface of the telescope to the instrument. But we can, I think, something that looks kind of like this folded configuration, sort of like the picture that Brad showed from the some early designs for WFOS, something that looks like that, but in the Cassegrain envelope. That seems like one of the more practical things to start with in terms of the optomechanical layout. And that's the first thing we're going to look at, I think, is whether that could work.
Josh?
So Chuck sort of touched on part of my question, which is for GLAO, if we wanted to make this GLAO compatible, how difficult is it going to be to pack the focal plane with both a MOS-sized field of view of 6 or 7 arc minutes and wavefront sensors? Are those two in conflict?
That's a very good question.
They have to figure that one out, right?
Yeah, so it depends how out of focus is the laser beacon going to be at the position of the focal surface of the instrument. That's one thing I don't know the answer to for Keck. We know the answer for TMT, and it was kind of scary because the footprint of the sodium beacons is something like this big around at the position of the focal surface. So it has to be, you know, everything has to be protected from. I mean, it's a good reason not to have a square field of view. Probably want to have something that looks rectangular, with the long axis being along the slit, and you use the extra real estate for fitting in the laser guide star wavefront sensors.
And there are technical reasons why VPHs would work better in that kind of configuration as well.
Yeah, so the one thing that about VPHs, they're great for fiber spectrographs because your fiber slit has the same camera field angle more or less along the slit, and so you get the same spectral response at each position. With VPH gratings, they care a lot whether you're close to the Bragg condition or not, and they fall off much faster than people are used to thinking about reflection gratings and changing the tilt of the reflection grating. And you know, they become more or less useless after you get more than a few degrees away from the optimal angle. And it's not a huge field of view, so that makes things better. But the actual response function changes a lot more than people might be used to over the depending on what the transverse, you know, the direction perpendicular to the slit direction, where the objects are in the field of view. It's within, you know, it becomes more problematic the higher the resolution. becomes more sensitive. For low resolution, you can do very well with resolution of maybe 1500 or 2000, probably get full spectral coverage of, you know, with just a single VPH grading on each side, assuming 2 channels. And then you have infinite flexibility to tune things up for smaller spectral ranges with higher dispersion gratings, which is, you know, is what KCWI takes advantage of, and it works really well for the KCWI case.
I have a question about that, Chuck, and that is, that implies you have to articulate the CCD then to get the...
Yeah, unfortunately, I think unless you just build in a fixed format that's designed from day one and nobody changes anything, I think you have to have articulated cameras and control the tilt of the grading.
And that sounds challenging at Cassegrain.
Yes.
That's the biggest challenge, I think, mechanically speaking.
So we're about halfway through, so I thought I would move from the kind of discussion of what you want LRIS to be to what would you do with certain capabilities. Now we've actually already, you'll see when I share my screen, we've already covered some of these topics, but I'll do this anyway. So, right, so the question I was going to ask folks was, you know, what kind of science would you do if you had the following capability? So the first one is this idea of if we could deliver to you an LRIS that also, using a VPH grading, so it's a high efficiency, could deliver a resolution of 20,000, you know, what kind of science would you do? John's already touched on this, and someone contacted me via Slack or via email actually about this. So that was one thing. Another question is, if you had the sort of GLAO, 0.3 arc-second seeing at say 700 nanometers, what would you do that you couldn't do now with LRIS? What kind of science does that open up for you? And of course, this is a nice thing where the combination of the 0.3 arc-second seeing and the RF 20,000, now, you know, Chuck says that, pointed out that you need a slicer with something like KCWI, but now we're delivering on axis something on the order of the slit size you need. So you could just use multi-slit. And then the final thing is that there's new technologies out there potentially for detectors that work like CCDs, but have much higher quantum efficiency. They don't have the silicon cutoff because they're not made out of silicon. So you can possibly get maybe, you know, 50% or 40% absorption past the place where silicon becomes transparent at 1080 nanometers. So you might be able to go out even into the middle of the J band. So all of a sudden now you have a spectrograph where you could potentially go from not just the blue optical cutoff or near UV cutoff that we currently have with LRIS, but could go much, much redder than you can with the current CCDs. So those are the kind of questions I was going to ask folks and see if anyone had any kind of pie in the sky ideas like, oh, that would let me, you know, the combination of these things would let me do this really interesting science result. Because I'd love to hear from folks about what that, you know, could do. So I'll stop sharing my screen.
Brad, what is that technology that you're referring to? Are these doped CCDs or are they CMOS infrared-like detectors?
Connie can actually speak about this a little bit better than I can, but they're germanium devices.
Yeah, they've been talking about these for 20 years and I haven't seen evidence that they exist, do they?
This is why it's pie in the sky.
Okay,
No, not
fair
yet.
enough.
Okay, Matthew has his hand up.
Yeah, so I think the 20,000 resolution mode would be very interesting for as an option to high res. And if you, I know the wavelength coverage wouldn't nearly be so large, but at the throughput and multi-slit mode, one could potentially do several setups on the same multi-set of objects, like 5 or 6, 10, 12 objects, and come out way ahead at this resolution and exposure time efficiency.
As long as you get light down 0.3 arc-second slits.
Yes, that's right. So it's sort of a combination of GLAO and the high resolution mode would be incredibly powerful for compact sources that, you know, are small enough to fit in that field of view.
Yeah, it seems like it would be attractive to people who work on faint stars.
Yep. Mm-hmm. Extragalactic, you know, M31 kind of object by object.
That's a good point. Has anyone ever thought about the difficulty of actually keeping objects in narrow slits over a significant field of view? I mean, there's the refraction term that you can't get rid of with an ADC that happens just because of a change in the effective plate scale.
Yeah, and your flexure has to be that much more controlled.
But at this high resolution, I'm not sure, you know, you have a smaller band pass, so you may not care quite as much. As long as your guider is in your band pass, you may not care quite so much.
I guess I'm worried just about, you have to design a mask with the slits in a particular place and the objects move as a function of zenith angle relative to one another over an 8 arc minute field of view. And that the amplitude is, you know, at the level of 0.1 or 0.15 arc seconds, so we haven't cared about it that much yet. We only worry about atmospheric dispersion, but I guess, I don't know, what's the right way to refer to this? People who do fiber spectrographs have to worry about this a lot. You can't use the same configuration for fibers at zenith that you would at an air mass of 1.5.
Right. So it would make masks more difficult and slitlets maybe a little more useful.
Yeah.
You could even move the slitlets over the course of the exposure.
Right.
Oh man.
Brad. Well, no, I was just thinking if you had multiple setups or wavelengths that you wanted to cover, and you were finished with your first one at zenith, and now you're, you know, a little bit over 1.2, you know, you might want to reconfigure, have a different slit mask because you're at a different wavelength.
Right.
Yeah.
So,
I think people have sometimes done this just because of you know, differential atmospheric dispersion with DEMOS if they want to use narrow slits, and
yeah.
it would require more. You'd probably have to have a few masks per field to observe the same targets that would be used at different times.
Yeah, we'd add another variable to that whole optimization, maybe a couple.
I wonder if there's a way, I wonder if there's an optical way of fixing the plate scale of the delivered by an AO system. Maybe somebody knows the answer to that. I mean, what do you do to have a consistent plate scale for, like, multi-conjugate adaptive optics.
Randy is, I think, the closest person I know of to an expert at this.
Yeah, well, all of the Keck AO systems are extremely small fields of view, and we don't have to worry about this particular problem. But I think I'm thinking in real time. I'm wondering if you can do it with the deformable secondary to just add a little bit of.
Yeah, that's what I was wondering too. Yeah. I'm not sure it's in the right place to introduce that kind of.
Right.
Anyway, something to think about.
In general, I you know, Brad, you said, what can you do with a 0.3 of an arc second seeing over the large field of view, and certainly that's gonna really boost the sensitivity, and that's gonna open up all kinds of new science cases, both for imaging and spectroscopy. But I think I think the complexity of making an instrument that works both with ground layer AO and without ground layer AO might be extremely challenging, because you want your plate scale and you want your slits and all that to match the ground layer AO, and then switching back and forth between the two, with maybe you can do it just with binning and just with different masks, but I don't know. I think you're going to want different instruments for the two different cases, would be my guess.
I think the only thing it would make, I think if this instrument were built, it would just have the space allocated for the wavefront sensors and things like that, and to be added later if we ever get to the point where we have an adaptive secondary, and it would have to work as a seeing limited instrument in its initial. I'm just guessing about the relative time scales of these things. But I mean, what would you do? I guess you would. So one issue I thought might be worth discussing is whether the optics and the current cameras on low res are good enough to go on to be reused on a new instrument. I'm pretty sure they are good enough on the blue camera, but I'm not sure about the red. Do you know, Connie, much about the red camera? It was designed way back in the 80s, and so before anyone knew that you could get 0.3 arc second images.
I don't know, but that feels like a study that we could at least think about trying to do and deal with as prep for this.
Yeah. But I think you could handle quarter arc second slits with the blue camera as it is now.
What about quarter arc second imaging?
Yeah, I mean, when you take an image of the slit mask with pinholes, you get 0.23 arc seconds full width half max for the blue side. I mean, that's basically, that was how it was spec'd out, more or less. I mean, it wasn't written down in that form, but that's what it turns out to be, to get. I think it has less than the image size. What is it? RMS image diameter is less than 35 microns or something like that.
As far as the focal plane scale, I think that was Randy's point about GLAO versus not. the cameras are already, at least on the red side, they're pretty close to f1, and the slit and the PSF are really oversampled. And I don't think it's not clear you'd want to go very much faster. So I think you get okay sampling for those tiny slits just because it's hard to get, it's hard not to oversample the seeing limited PSF.
Yeah, I think the sampling with a typical camera like we've built for other instruments would be about right for the high resolution mode.
Yeah.
Not binned, of course, like everybody uses for observations now.
Yeah, it's the very reason they bin, and you really couldn't imagine trying. It doesn't seem like the right place to make this hard, I guess is what I'd say. So you stick with about the same speed camera, which means you'd oversample the seeing limited PSF the same way.
Yeah. So I'd like to ask the people in the room whether the imaging is important to maintain, because it's a little bit more complicated to get imaging built into the instrument with VPH gratings.
For me, LRIS is really the only optical imager on Keck that I can use.
Yes, now certainly that's true. Maybe someday we'll have KWFI, which has got a session later this afternoon. But yeah, I mean, it's a little bit awkward that imaging with LRIS and MOSFire, for that matter, are the largest field imagers we have in the optical and the near infrared, respectively, and they're not very large. But we don't want to lose that capability. I mean, it's still used a lot.
Well, for Melissa's case, the field of view of Quiffy is kind of overkill. I suspect she would.
Is that what it's called? Quiffy?
What would the field of view be that?
It's going to be
of order of degree.
I mean, that would, if the object is on the verge of getting lost, that would be helpful, but it's not necessary for my case. But I'm a very small percentage of your users. I haven't not actually triggered any of my TOOs because I live 7 hours away from the observing room.
Yeah, I think, but the one thing about KWFI is that since it will be optimized for imaging, it's going to have fast readout of the full array, and it might have less overhead, even though it's a larger format than an instrument primarily built as a spectrograph.
Mm-hmm. And it might actually have exposure time calculator too.
Well, exposure time calculators are useless anyway for ground-based observing. You can't believe what an exposure time calculator tells you because it all depends so much on the conditions.
As someone who has been radial velocity adjacent, I will contest that remark. Josh
you can
has
kind of get, if you use it enough, then you know how close it will be. You know, I usually observe 6 nights or 4 to 6 nights a month on our telescope, so I know what they can do. But so a tuned exposure time calculator for an instrument that I don't use very often would actually be helpful.
Josh?
Just real briefly, Chuck mentioned a number that he got from Mark about 40% use being long slit. Anecdotally, I feel like it's a bit higher than that these days, but that got me thinking. I had a quick side conversation with Mark. I'm going to redo Mark's analysis so we can break down imaging MOS and long slit just to see what's going on. So if anybody wants to see the results of that when I can get some time to do it, shoot me an email, and I don't know. Anyway, if you're interested, let me know and I'll try and do all that.
The one thing I immediately thought when I looked, Mark gave me this huge data dump, is that, of course, a fair number of those long slits are people who are doing mass, but because this was the number, I think, of exposures, not the amount of exposure time. And so then you have folks who are using the beginning and the end of the night to take calibrations that they use to calibrate their mass. So it's, you know, the science case we really want to pursue are folks who, I suspect, are folks who want to do rapid follow-up of interesting objects that we find with all these robotic synoptic surveys. And we want to make sure we support those, whether or not, you know, everyone gets their favorite metal poor subdwarf spectrum efficiently or not is a little less of a priority. Aaron has his hand up.
Josh, when you're doing that tally, would it be possible to also include polarimetry as a separate category?
Yes, I'll try and be as complete as I can, and especially breaking it down by exposure, by unit of exposure time, by unit of clock time, all the modes I can think of. I'll definitely try that. Polarimetry, I mean,
it's very small.
By a scheduling issue, less than an observer choice issue during the night.
Yeah, I was going to ask if polarimetry is considered for LRIS-2 at all.
I mean, the key is to, you know, make sure we replace LRIS, and that's part of LRIS. So it is something that we have to consider. This is one of those cases that Aaron and I have started discussing this on Slack, where I don't know very much about what the needs are, the science needs are. So getting help from folks out like you who have science interest in it will help me inform what the needs are from the instrument design standpoint. That was maybe a little more complicated than it needed to be, but I hope I got my point across.
Yeah, so if you could write down what the requirements would be for what you would want to do with such a capability, that would be very helpful.
Yeah, I also think that some of the existing polarimetry components might just be able to be recycled straightforwardly into a new instrument, like the beam splitting crystal.
But it must put some constraint on field size.
Oh, yeah,
right?
it does. For polarimetry, you always have a very tiny field size. It's 20 arc seconds or something like that.
Okay.
Yeah, but we've always lived
no.
with that. That's fine.
Okay.
Where is it? You can't. It's not remotely configurable. Putting it into polarimetry mode.
Not in LRIS, but if that would be a great thing to have. The cast spectrograph at LIC has that capability where during the night you can just hit a button and it'll put the polarimetry module in beam or take it out of beam. But with LRIS, it's in or out for the whole night.
Where does all the apparatus go when it goes in?
Where does it go?
I mean, like where is the beam splitting?
All the polarimetry, the polarimetry module happens. That's before the light gets to the slit, so it's somewhere above the slit.
Okay.
I don't know the exact physical layout inside the instrument, but you split the beam into two orthogonally polarized components before the light gets to the slit.
Does it require optics other than the beam splitter? I mean, do you have to?
Yeah, there's the beam splitter, and then there is basically a filter wheel that has polarizing filters, and you need to have the ability to rotate the wave plate.
Okay, so this is all up. It's a module that's up in front of the slit.
Yeah.
I see.
Does it move
I'd like to see
focus?
what that looks like.
Does it move focus? Do you have to refocus?
It must.
I think at LRIS, since it's in beam for the whole night, you focus with the polarimeter in beam, and so that we're never changing back and forth during a night.
I'm just amazed that CAS can do something that LRIS cannot.
It takes somebody to be interested enough to take it on as a project.
Fair enough.
That's how everything gets done at Keck as well as LIC.
It probably helps that the former director wanted this to happen. Okay, does anybody else have any questions they'd like to ask? The meeting has gotten very sprawly, but that's fine.
I have a question. How's the new red side CCD going?
It is going, and we were asked to speed it up, so we will try and do so. One of the things I guess I should say is that I hear loudly and clearly about the readout speed, and we will hopefully improve that on the red side.
Well, it's always been in part because you couldn't use some of the amplifiers, hasn't it? I mean, it's nothing about the electronics that's different, is it?
On this particular set of CCDs, it was to reduce the noise. I'm happy to give more details, but basically the clock feed through is so strong on these CCDs that we had to wait a long time for it to settle for every pixel to keep the read noise down.
I see.
So we will hopefully these detectors will be better behaved, and we can speed it up. Chuck, you said 40 seconds in the mode that everybody uses for the red side. Is that, how many amplifiers is that?
That's 4.
Okay.
4 amplifiers.
So 2 per
2 on
chip.
each. Yeah.
Okay. Thank you. And that's the mode that most folks use. Okay.
Yeah, that's 1x2 binning.
Yeah.
Or 2. I think it's the same for 2x2 binning, roughly.
Okay. Yeah. Because there's one direction that makes it go way faster. So
yeah.
Okay. And so it's binning in the fast direction, and with 4 amplifiers. Okay, good to know. Thank you.
This is Matt Radovan. I just have a few quick comments I'll make. Chuck, with respect to your question about where the laser guide star focus follows, I put the number in the chat. Phil Hines is leading a study to look at the new Keck adaptive secondary mirror, and they seem they are worried about this issue that, of course, all the existing instruments will need wavefront sensing if they're going to take advantage of that. So I think there's some help that this study can tap from that group. The other thing I would say is that with respect to flexure and articulating cameras, from the mechanical engineering standpoint, there is a difference between 2 discrete camera positions and more than 2. With respect to choosing resolutions and using VPHs and over what wavelength you run, if you have a mode where it's an A or a B mode, that makes for potentially easier options for the mechanics than 3 or an infinite amount. So ESI takes advantage of this fact. ESI actually has optics that move. They move in and out or to AB positions, and it has super high stability with its open loop flexure compensation system. So if you need more than 2 camera positions, we'll give it to you. But if you can work with 2, it's a nice simplification.
I don't see how people would ever. I mean, that means you can basically work with two different resolutions, and that's it. But you have to change the camera position. Just at high resolution, you need multiple gratings and multiple camera positions, I think, to be efficient.
Yeah, Jason thinks you can get you the full wavelength coverage in one position at R of like 2000 or something like that. This will be a
Yeah,
question
that's right.
But it's
No,
going to
that's you can get it at that kind of resolution. I agree. That's the mode that most people will use, I think, for the things that people have typically used low res for. It's although it's a little bit higher resolution than what we currently get in that mode. But
I still think
I don't.
Go ahead.
Yeah, I mean it's possible, and if it's the only way to make it stable, then people will have to accept it, I guess.
No, executed properly, Chuck, we can give you a system that gives you the stability of you know, the best we've done for a number of camera positions. I'm confident that that's doable. So that shouldn't be a limiting factor. You should make the request for what you need scientifically, and we'll figure out how to get it done. And with the open loop flexure compensation system with proper attention paid to details, it should be able to perform as well as ESI.
Yeah, it's probably one of the questions I should have asked at the beginning and didn't. Is ESI enough? Do we need to do better than that?
There's nothing
enough
better.
For enough what?
In terms of wavelength stability with the flexure compensation system.
I think it is. Yeah, I think ESI and MOSFET both perform at the sort of 1/10 of a pixel level. In fact, over an observation at least, and the repeatability is better than 1 pixel for MOSFET. I know that. I think that's about what you would want to shoot for. One hopes, because if you have multiple channels and continuously variable everything like you would in one of these VPH camera systems, you would hate. I mean, it's a mind-boggling mechanical system to think about how much motion you would need to have control over to keep the image stable on both cameras all the time at any gravity angle. So it would have to be.
Oops, sorry, Chuck.
Yeah, sorry.
I'm just wondering if Josh is going to make a comment about MOSFET and FCS and.
Sort of, yeah. I was going to ask. We've talked about open loop FCS. What are the advantages, the disadvantages of closed loop? Because I just worry about. So when doing the MOSFET or FCS, you basically build a 2-dimensional model for each mode, which is only 4 commonly used modes, basically. If we're talking about a lot of mechanisms that have continuous variability, all of a sudden your parameter space just blows up for the FCS if you're doing it open loop. So how do you train that to go to closed loop at that point?
Machine learning, of course.
Where the machine is some poor postdoc who sits in the lab for 5 years trying every conceivable position.
I can't feed him that much data, probably.
Yeah, I think that kind of argues for having some kind of closed loop system when you have that much complexity.
So I'm going to disagree with Chuck here and say that the best performing systems on any 8 to 10 meter class telescope instruments are open loop systems. And the 2 best are, as far as I know, Connie's shaking her head. I'd love to see another example. I think, Josh, the answer is you got to get rid of the variability. So variability is hysteresis. So as long as you build a system without hysteresis, then the complexity can be handled in doing the mapping of the instrument. And I think that the WFLOS team has developed some pretty good models to simulate this. So I'm less concerned about this. I think again, the devil's in the details, and the details just have to be well executed. And that's sort of what limits the performance of LRIS right now. They just they weren't paying attention to, and they didn't know enough at the time to address these. And we've learned from the instruments that we've built over the years.
Yeah, well, it's 10 times easier to keep ESI stable than it is to keep low res stable, because it's got much less going on inside. It's just one reflection off a collimator with a fixed grating. But with low res, you're changing crap all the time, and everything is different.
Yeah, but the problem is when you make the changes, that's not repeatable, right? So it's not a function of the change, but it's a function of the details of the change. So that's where you have to pay attention, and that's what we'll have to demonstrate and get right. But I would submit that it's kind of like saying it'd be impossible to make a 10-meter telescope with 32 individual mirror segments and keep them all hooked together. They're all moving all over the place, right? And that system works. So this was a discussion that I had over and over and over again with Jerry Nelson, and he firmly believed there was never a reason to go in. You're better off if you can make a open loop system work, because it forces.
I couldn't agree more. I'm just worried that you couldn't.
You couldn't
calibrate if you couldn't calibrate it well enough if you had an infinite number of possibilities. But it's probably doable. That's certainly what you would try to do, at least until you discovered it was making life too difficult.
That probably answers your question, Josh. That, yeah, I mean, somebody went through and counted the lines of code the other day in the FCS system for DEMOS. And I think they got like 15,000 or something.
I think the biggest argument for having an open loop is just that it's easy to make it always on, and it's much tougher to get things right when you're doing your calibrations and all that kind of thing. If I understand the DEMOS system, it kind of needs starlight, doesn't it, for some of the thing, or at least skylight to do some of the.
No.
It's lamp lines, but
yeah, you need to have a wavelength solution that gives you lamp lines on the chips that make the correction.
Yes, so DEMOS has 4 fiber optics in the focal plane at the 4 corners that produce F-15 little artificial stars that are fed with thorium argon through the system. So there is some level of thorium argon flowing through that instrument that's outside the active field of view.
So one other implication of this is that in the current LRIS setup, partially because you have to focus every single mode, it's extremely demanding on afternoon setup time. Part of that is because you cannot start until you get the full telescope release and have it pointed at some vaguely practical elevation. If you have an FCS that works at, say, 0 elevation, you can do all this before release, but that's also pushing it for an open loop system.
That's a good point.
So actually, people focus low res too much, because almost all of the different optics that you put in there, it's all in the differences in focus are in the noise, and you're just wasting time doing all that focusing. I've always used one focus for all the dichroics, the clear, everything is within uncertainties, the same focus, except for when you change interference filters for imaging. And I've told every successive astronomer in charge this, but no one believes me.
Who at Keck knows the most about the guts of what's inside LRIS? Like if you asked them, Chuck, what's the detail look like of the dichroic transfer mechanism? Who's the master?
Well, the person who designed that mechanisms is Bob Weber.
Okay.
But Mark Cassis, I would guess, is the person who knows the most about the innards because he was for many years the LRIS specialist.
The original low-res design, are any of the people who worked on it still working, or are they all gone?
I think Mike Carr still works for Jim Gunn.
He's retired.
Oh, is he?
He's
Okay.
retired. Yes.
So Bob's our guy. Okay.
Yeah, I mean, the blue side stuff, the red side stuff, there's nobody's still alive that, or still active in engineering wise, who worked on that.
I ask only because I think maybe with a discussion with Bob, we can learn a lot about sort of some of the limitations and the of what's going on in there. So I can have that conversation with Bob.
So those mechanisms are not responsible for the flexure. They're actually very repeatable, that like the dichroic transfer and all that kind of thing. It's most of the flexure comes from the snout, the front end of the instrument where the mask is. It's like an 8-foot throw to the collimator mirror, and it just kind of flops around. And you can tell because when you cross the meridian, all of a sudden the entire spectrum shifts by about 10 pixels.
But Chuck, you just told me that there's mechanisms in there that go in and out and change that don't contribute to the flexure of LRIS. So I think that that's my point. I think that if you did everything like what Bob did, maybe
that's right. But I mean, it's less. The dichroic is just a thick plate of glass, so it's kind of hard to make it do anything.
I understand, but I'm just, again, we have to do better than was done on LRIS. And I think
that's the whole point of redoing it. Yeah.
Right, a lot better.
Well, okay, so it's 2:23. The next session starts in, sorry, that's California time, in 7 minutes. So I'm thinking that maybe we'll just call it a day. I did get a lot of feedback from folks. But, you know, if you have anything that you would like to say that you want to go to me, feel free to send me an email or use either the Slack channels, the one for this particular breakout session or the one for my talk earlier today. I've also gotten feedback there, and you know, feel free to ask me questions, like including things like, Brad, I missed your email, so could you send me your email, Jess? And I would love to get, you know, more input from many of you who were pretty quiet during this session if you have things that you want to know or want to ask. And otherwise, thank you all for attending, and enjoy the rest of the meeting.
Thanks, Brad.
Thanks, Brad.
Thank you.
Yeah, thank you.